Right, from the looks of it, there's no one else currently joining, so let's begin this webinar. Thank you everyone for coming to today's ARCHER2 webinar. Today we have Alexei Bobrik, who's coming to talk about using HPC computing to study the exploding, formation, and disentangling of stars, or exploding, forming, and disentangling stars. Alexei is currently working at the University of Malmo in Sweden, though is currently based in Lund. And we'll be talking about a collaborative project that he's been doing with people at the University of Birmingham. With that, I think I will let Alexei take it away.
Thank you so very much, Julian. And let's get started and dive directly into the world of astronomy. So let's see. All right, so I'm going to be talking about basically applying high-performance computing to problems of astrophysics. And I'll talk about that by going through a few of the studies, which in particular I've done with quite many very good people over here. One of them being Silja Tunen, who was my host when I was visiting the University of Birmingham recently. And at that time, we were using the high-performance computing at EPCC Centrum, and I'll talk about that as well. So in all my presentation, I would like to convey three basic ideas, I would say. So first of all is that astronomy really is very diverse. Somehow, whilst it's one topic, it contains a lot of very different types of objects which interact in very different ways, and that leads to very different types of mathematically and numerically different types of problems. And that comes along with that other idea that stars continually do something. So they form, they make complicated systems, puzzles, and they explode all the time. And in principle, many of these things we are still trying to understand. And the third key point I would like to convey really today is that astronomers really heavily rely on high-performance computing to solve their astronomical puzzles. And I'll showcase basically how the high-performance computing is instrumental for astronomers by going through three very different types of problems. And the first type of problem is about our recent study of the evolution of subdwarf B stars or subdwarf B binaries in a galaxy. And so here on the picture, there is a picture of a galaxy, and I bet everybody has heard what a galaxy is before. So galaxy is a large group of many stars, and this is in particular M31 Galaxy Andromeda, which is thought to be kind of similar in structure and appearance to our own galaxy Milky Way. And on the left, you see a subdwarf B binary, and don't be afraid of the name. I'll explain it in 1 second. But basically, this study is really about the fact that actually the life and formation of those subdwarf B binaries is very much connected to the life of galaxy, and that has not been understood until recently. So subdwarf B stars. It is basically this astronomical nomenclature, so it's just the way people name stars. So basically, when people say B, it means that it's blue, so you just color blue. When people say that it's a subdwarf, it means that it's just small compared to regular stars. So in other words, it's blue stars which are small compared to regular stars. So those subdwarf B stars or SDB stars are those blue small stars. Typically, when astronomers try to visualize all the possible stars which they observe, they make this so-called Hertzsprung-Russell diagram. And it's a diagram where on the x-axis we have something like a color, so like blue to the left, red to the right, and on y-axis we have something like brightness. And like on that diagram, people visualize all sorts of stars. For example, main sequence stars like the sun, also giants, which are red giants, and also like on that diagram, one could see that those subdwarf stars, I mean, they are subdwarf B stars in particular, they are blue and they are just less bright than typical normal stars like the sun or main sequence stars. Subdwarf B stars are helium burning, so in other words, they are not just small, they're also burning helium in their cores, which is different compared to the sun, which is burning both, which is burning mostly hydrogen in the core, and therefore those subdwarf B stars typically end up being very small and bright. And additionally, those subdwarf B stars, they don't have almost any hydrogen in them, so which is unusual because typical material of which the stars are made of, it typically contains a lot of both hydrogen and helium, but in this case these stars are made almost entirely out of helium, and they burn only helium, they don't have hydrogen. And these subdwarf B stars, they are approximately 10 times smaller than the sun, and they have typical masses about half that of the sun. And they live astrophysically short, only 100 million years. For comparison, the sun lives or will have lived by the end of its life about 10 billion years. So these stars are very short-lived compared to typical stars like the sun. And these subdwarf B stars form in a quite peculiar way. So here is basically a diagram which basically explains how that happens. So imagine two stars, two yellow stars, which are somewhat similar to the sun. So one of them is a bit more massive than the other one. These two stars are initially in a binary. The binary orbital period is between 100 or 800 days. So it basically takes the two stars about, well, few months to a few years to make a full orbit around each other. And then if you follow what happens to these stars, so over some time, the more massive star will evolve and become a red giant. And it does so because it has burned all its nuclear fuel in the center, all its hydrogen fuel in the center, and it starts to burn hydrogen in a shell surrounding the central core, whereas the central core is made of helium now. So at this point, the star is said to have entered the red giant phase. It becomes much bigger in size, and its core is made entirely out of helium, but it doesn't burn any helium. It just burns hydrogen on top of the helium core. And as this red giant star expands in the orbit, the companion star, main sequence star, will start to gravitationally pull the material off from the red giant, and the material will be kind of landing onto this main sequence star. And as the time goes, the mass transfer rate, or the rate at which the mass is lost from the red giant, might increase and get faster and faster. And in the end, under proper conditions, if the core of the red giant was sufficiently massive, that core of the red giant made of helium might ignite and become this SDB star. So in other words, the overall sequence is that, well, there was this main sequence star, then it formed a core, a helium core. The helium core did not do anything. By the time the red giant was evolving, and whilst it was losing mass, that core grew up in size. And then by the time the red giant lost its envelope, like lost the material from the surface, its core managed to ignite helium, and whilst all the hydrogen was lost from the surface. And in the end, we just end up with having a core of a giant which is ignited helium. So in other words, just put simply in one sentence, subdwarf B stars are cores of red giants which have been stripped and which have managed to ignite helium. So those objects actually have quite a peculiar history. And these subdwarf B stars have actually found quite many uses in astronomy. So one of them is that subdwarf B stars really probe the evolution of red giants. For example, I mean, just this scenario for their formation is relatively simple. It just has maybe like 2 steps. I mean, so red giant has formed and then has lost its envelope, and there you go, you have an SDB star. So in other words, the system has had relatively simple evolutionary track compared to many other astrophysical systems, and therefore these binaries probe red giants. On top of that, the subdwarf B star is bright, and it can be observed and characterized through their spectra. So are their companions. So actually, when you have 2 stars which are bright and can be characterized spectroscopically, they're called double lion binaries, and they can be quite well studied, and their orbits can be obtained to quite a good precision. Then, as I mentioned, the formation channel is quite simple, and therefore one could use those subdwarf B stars, or at least their orbits, to study overall the process of how does the red giant lose or get stripped, lose mass or get stripped by the companion, and how does the mass generally get ejected, or what happens to the mass which has been stripped inside those systems. So these binaries, the outcomes, subdwarf V binaries, are quite good probes of what happens when red giants interact with other stars. And recently, subdwarf V stars were shown to have been to be quite good probes of common envelope evolution, and that's basically when the red giant and other stars merge quite dramatically, and I won't go too much more into that. And now the recent use of these subdwarf V stars has been that actually they are quite valuable in probing the galactic history, and actually, as a matter of fact, they're the first binaries which actually show that first post-mass transfer binaries which show the effects of galactic history. Finally, those subdwarf V binaries can be of different types. They can have long periods, short periods, or they could be single. We're only focusing on long period SDB binaries. In other words, binaries which have main sequence companion. So SDB stars which have main sequence companion and which have orbits between a few hundred and like between about 500 and 1500 days. So like typically a few years orbits. And now the thing is that if we try to detect all the subdwarf V stars in the galaxy, it takes basically time. So I mean, they have orbits of order of a few years, so one has to really follow them spectroscopically for several years and try to basically characterize them. And that's a bit laborious process, basically. So right now we have orbits for about 20 of those subdwarf V stars. And here on the plot, you see orbital period on the x-axis and mass ratio in the binaries on the y-axis. And mass ratio is the mass of the blue SDB star divided by the mass of the companion main sequence star. And on the plot, all the dots are all the observed SDB binaries. And basically, we could see that there's some kind of correlation between the mass ratios of SDB binaries and the orbital periods of these binaries. And that seems to be all good, but the problem was that if one were to take a detailed stellar evolution code, such as a mesocode, this mesocode basically evolves the stars in detail over time. It's a spherical symmetrical code which evolves basically all the properties of stars, such as their composition, temperature, density, everything you can imagine over time. And so basically we kind of could say with this mesocode that we know everything about the star quite well for, I mean, the course of its evolution. And people have been trying to explain this period mass ratio correlation by using mesocode quite many times. And the thing is that, you know, the formation scenario for these binaries is relatively simple, but it was always very hard to explain this exact relation between the mass ratios and orbital periods. I mean, specifically when people were just trying to simulate those main sequence binaries becoming red giants and igniting as SDB stars, they always ended up with periods or mass ratios somewhat different from the ones which are observed. And there have been quite many attempts to explain that. Specifically, maybe there's something about the way the red giant gets stripped. Maybe there's something about the way mass is lost from the binary when the accretor takes it. Maybe mass is ejected and takes away angular momentum from the binary, so that affects the orbit or something like that. So there have been quite many explorations, and they all have actually failed to exactly explain this mass ratio period correlation. And apparently nowadays, or specifically as of since year 2019, this correlation has been actually explained. And the explanation to that comes from, well, basically the effects of galactic evolution. So there we are. So here is the connection. So here on the top left, we see the subdwarf B evolution scenario or formation scenario. In the bottom, we see this image of Andromeda Galaxy, which, by the way, will merge with the Milky Way galaxy in 4 billion years or so, which is, by the way, okay, because there's going to be many other horrible things happening to the Earth before that. So, but if you, yeah, so anyways, distraction. But so in other words, so we see this subdwarf B binary formation and the image of the galaxy, and the point really basically is very simple. So subdwarf B stars actually live in the galaxy, and well, there might be some connection in there. And apparently that connection helps to explain that mystery with the periods and mass ratios that you mentioned in the last slide. The thing there is that if you think about those subdwarf B stars, I mean, the effect comes from the fact that the objects which turn into subdwarf B stars, they are kind of at the end of their main sequence lifetime, and that main sequence lifetime is sensitive to the mass of the star which becomes red giant or which reaches its end. So in other words, if we go through this scenario and imagine that the starting star was approximately 0.8 solar masses, 0.8 solar mass star tends to live very long. It tends to live for almost 10 billion years before it becomes a red giant. And it means that if a 0.8 solar mass star or sun-like star formed an SDB binary, it means that that star was born really long time ago because it really needed time to become a red giant. And if you think about how did the galaxy look like about 10 gig years ago or 10 billion years ago, we realized that the galaxy was much more metal poor than the current galaxy. So in other words, if we had a subdwarf B star, which comes from a solar-like star, then initially it had a low amount of metals in its atmosphere. And that actually has quite a big impact on the radii of red giants. As a matter of fact, if you take a star which was formed in a galaxy 10 billion years ago, then the red giant will have radii about 30% smaller than it would have if it had been born currently. So put in other words, if one took a red giant at solar metallicity or at present day metallicity, or if one took a star which will become red giant from forming right now today with solar-like metallicity, then it will become bigger than a red giant which formed or formed from a star which formed a long time ago. Now, if we consider the subdwarf B progenitors which were initially higher mass, so for example, if a star initially of 2 solar masses evolved through this scenario and became a subdwarf B star, it would mean that such star was formed not so long ago, because 2 solar mass stars live only for about 1 billion years instead of 10 billion years. So it actually formed about 1 billion year ago. And 1 billion year ago, the galaxy didn't have a metallicity which is very different from today. So in other words, 1 billion year ago, the metallicity of the galaxy or the amount of metal in the galaxy was about the same as presently. So in other words, we have this picture that if we had subdwarf B stars which formed from low mass progenitors, they inherited low metallicity. If we had subdwarf B stars formed from high mass progenitors or high mass progenitors, then they inherit high metallicity, and that metallicity affects the radii of red giants, and that really physically is simply because if we have some amount of iron in stars, as opposed to when we don't have it, iron makes or metals generally make the envelopes of stars opaque, and when the envelopes of stars are opaque, then they have harder time propagating radiation out of the cores, and so basically the convective motions in these more metal-rich red giants become more vigorous, and the red giants eventually become just larger. So, and that actually has an effect on the final periods, because if we have stars which have larger red giant radii, then the binaries interact basically at different separations or in a different way, because red giants are different. And if we account for that metallicity effect just through the quite normal models, standard models of evolution of these binaries, we find that the fit in this period mass ratio relation becomes very good. So specifically, here are 4 plots of this period versus mass ratio relations, and the gray squares indicate the subdwarf B stars. The observed subdwarf B stars, and the blue circles indicate the simulated subdwarf B stars, which are simulated with MESA. MESA, this detailed stellar evolution code. And basically, if we check what happens to a sample of MESA simulations if we initialize them at solar metallicity, so metallicity like the sun, which is very typically done in binary population studies, we find that, as I mentioned, that it's very hard to explain the observations with detailed stellar simulations. And likewise, if we take low metallicity for our initial population and simulate them through the code, we find that the observed periods and mass ratios don't really match the observations. They all are shifted somehow over there. And even if we take the distribution which is uniform in metallicities from like low values in the galaxy to moderate values in the galaxy, present day values, then we find that the simulations do not really kind of sit on specifically on the observed systems. They kind of scatter all over the place, and they don't explain the observations just really well. And finally, if we really initialize the systems and initialize them with properly assigned metallicities, so in other words, if we take the stars which are from a long time ago and assign them metallicities from that time, and take stars which are from present day and assign them the present day metallicities, then we find that the MESA simulations actually reproduces the observed sample really quite well. Apart from those points on the left, which have slightly different origin, and ask me if you are interested later. But so the main sample of the sub-dwarf B stars is actually apparently is explained really quite well by just really setting up the initial metallicity correctly. And well, we thought, really, is it just a lucky coincidence or is it not? So we really just then decided to check ourselves, and we took the observed sample of those sub-dwarf B stars, so of these gray squares, and we have gone through literature, and after we did the simulations, and we have obtained there, or have found, or calculated, or summarized in a table their metallicities and orbital periods, and we have checked really what are the metallicities of observed sub-dwarf B stars versus their periods, and then we plotted on top of that the results from our simulations, and we were extremely happy to see that without any fitting, without any parameter tuning, we actually happened to have our modeled set sitting right on top of observations. And well, that was like a very happy moment for us when we were modeling the system. So basically, without any planning or intention, we actually found that our model reproduces the observations of metallicity and orbital periods really quite very well. So just a few reflections on this particular study. So first of all, I mean, basic conclusion is that we have indeed had demonstrated the origin for the period mass ratio relation for the first time. The paper got accepted to ANA and got even a highlight from the journal, because, well, it's a new connection between the stars and the galaxy. Quite importantly, we also formulate quite a strong case that such an effect, or this effect of metallicity on the radii of red giant, could also have an influence on other types of binaries wherein red giants are involved. In particular, it could be relevant to double white dwarf binaries, or so-called cataclysmic variables, which are made of white dwarfs and main sequence stars, for example, or symbiotic binaries which contain red giant plus a white dwarf, for example, and many other binaries which contain red giants, because red giants might be sensitive, or not might be, but they are sensitive to metallicity at which they formed, and that might be important for this or that evolutionary scenario. So actually, just this simple story could actually have quite many implications. And this is also the first time, as I mentioned, that the galactic evolution is actually seen through the binaries which have done mass transfer. So actually the first time of interacting binaries showing any effects or reflecting the effects of galactic evolution. And really, like, reflecting what actually enabled us to find the solution to this puzzle was basically the idea that, basically the effort we tried to do to actually conduct the grids of MESA runs, so these stellar evolution runs. So in other words, through exploring or visualizing the effects of different parameters on the simulated sample, we were actually able then to see which parameters are relevant to the to the observational data set. And in other words, I mean, we really, I think, gained intuition when we were able to run quite many, like hundreds or thousands of MESA simulations in parallel, and then analyzing them, and that way visualizing which parameters have which effect. And just to give a sense, a typical MESA simulation runs on a single core for, give or take, maybe a day or two. So I mean, basically running hundreds of thousands of those simulations is, well, is a moderately intense computational problem. So moving onwards, this story brings me to another story which is related to merging double white dwarfs. So merging double white dwarfs is quite an important topic, and that's mainly because it's connected to the so-called Type 1a supernovae. And Type 1a supernovae are, I think, quite very well known even outside of science community. Basically speaking, Type 1a supernovae are among the brightest explosions out there in the universe. So here, for example, is an image of a galaxy, and this is the galaxy. And here, this bright spot is actually a Type 1a supernova which has exploded, and actually at its peak brightness, it gets almost comparable to the brightest parts of the galaxy. And so, apart from that, these Type 1a supernovae, they are very interesting to us and galaxy evolution people, mostly because they are the dominant producer of iron group elements or iron group metals in the universe. So in other words, if you have anything metallic around you, for example, like a watch or, I don't know, a pen or something, then the metals in there very, very likely were actually produced in an explosion of Type 1a supernova, actually in actual physical, one of the brightest explosions in the universe. So it is these explosions which produce the iron elements in the Milky Way and around us. These Type 1a supernovae were also, or are also, used as an important cosmological problem. That's because they can tell us how far away they are, and also how well, they basically can tell us the redshift and distance at the same time, and this way allows us to reconstruct the evolution of the universe as a whole. And this way they were used to actually establish the cosmological acceleration in the first place, and which was later supported by other observations. And the thing is that Type 1a supernovae are thought to be detonations of white dwarfs. In particular, there are two schools where people. One school says that Type 1a supernovae are detonations of 2 white dwarfs, and another school says that they're detonations of 1 white dwarf, which has been accreted material. And there are also more details to these scenarios in principle. But today I would like to focus on detonations of 2 white dwarfs in a binary. So that's one of the 2 leading scenarios for Type 1a supernovae. And the reason why they are bright is that Type 1a supernovae produce a lot of, or mergers of double white dwarfs produce a lot of nickel-56, which then radiatively decays into cobalt-56, and that then radiatively decays further into iron. And then the energy deposited from this nuclear decay produces a lot of heat in the surrounding material, and that leads to the glow of Type 1a supernovae. So there it is. So here we are trying to simulate how Type 1a supernovae occur, and specifically in this study, we consider how. So here is an example of a simulation of 2 white dwarfs merging. These simulations are done with the SPH code called Water, which is developed by myself and our group. So here, every white dwarf of each of the white dwarfs. So in particular, in this video, a massive white dwarf of about 1 solar mass is accreted material from a less massive white dwarf of about 0.6 solar masses, and each white dwarf in this sort of code is represented by a set of particles representing parts of its material, and the animation shows the evolution of density over time. So, and these 2 white dwarfs, they kind of initially are brought together by gravitational waves, and after they are brought together, the more massive star or more massive white dwarf strips the material from the other white dwarf, and it does so progressively more and more intensely until it really distorts the donor star and finally disrupts it, as we see right now on the video. Well, these sorts of things are happening in the universe like all the time. So basically, white dwarfs essentially merge, and in this case, this simulation has been done with the hydrodynamical code, so we didn't model detonation in here, but in principle, during the merger, or again, depending on the model, the conditions for the nuclear detonation might occur, and those conditions then lead to the detonation of the whole system at once, and that whole system then basically blows off and produces that large amount of nickel-56, which I was talking about, and then eventually nickel-56 leads to the glow of the whole system. Now, the thing about double white dwarf mergers actually is that it was recently realized that the presence of helium layers on the donor and accretor in these double white dwarf systems actually is quite important. So if you think about the two white dwarfs merging for a second, then actually, let me stop the animation. So then actually the donor white dwarf is actually expected to contain thin layers of helium left from its previous evolution. As a matter of fact, so remember I was talking just recently about the subdwarf B stars. Subdwarf B stars, after they burn helium in their core, eventually become carbon-oxygen white dwarfs. And if one asks a modeler of subdwarf B stars, like what sort of white dwarf or what sort of object remains after the subdwarf B star burns up its helium fuel, typically the answer would be that we are left with a carbon-oxygen white dwarf with an uncertain but probably non-zero layer of helium, and which can be between 0 and roughly speaking 0.05 to 8 solar masses, depending on how you exactly, which models you exactly believe. But in any case, we believe that white dwarfs in quite a large fraction of type 1a supernovae, or the white dwarfs in quite a large fraction of merging double white dwarfs, contain helium layers on top of them. And the thing about helium layers is that helium material is very easy to detonate, and therefore the presence of helium might actually quite much change the way the whole system explodes when the detonation conditions are reached. And that's exactly the subject of our study. So generally speaking, there is this sort of diagram wherein on the x-axis we have the mass of one of the white dwarfs, and on the y-axis we have mass of the other of the white dwarfs. And at every point of the diagram, we basically see the outcome of what happens if we take white dwarf of one mass and merge it with a white dwarf of that other mass. And these sort of diagrams basically say that mergers of white dwarfs can actually lead to quite many different types of outcomes. And this is a diagram from Marius Den and others from 2014, and it very beautifully illustrates that, you know, if you take like somewhat massive white dwarf number 1 and somewhat massive white dwarf number 2, then, well, we quite easily produce type 1a supernovae. And if we take, for example, not so massive white dwarf, merge it with yet not so massive white dwarf, we produce other types of stars which do not detonate as a whole because the white dwarfs are not as massive, not as energetic. And this diagram was constructed on models assuming that the white dwarfs do not have any helium layers. And in principle, if one actually tries to base that same diagram on the models accounting for helium layers, we actually get a slightly different picture. And that's been a subject of our recent paper with Hagai Perez and Yosef Senati and Silva Tunen. And basically here we still have mass of one white dwarf, and here we have mass of another white dwarf, but we see that other quite different masses of white dwarfs lead to type 1a supernovae, and in particular we find that the presence of helium layer, well, basically requires us to rethink all the possible outcomes of white dwarf mergers, because actually that can be quite important for nuclear detonations. So that's this basic key point, which has been recently realized, that the presence of helium really requires us to rethink the typical double white dwarf merger outcomes. And what we currently are doing in that direction is that we simulate the white dwarf mergers with this SPH called water, which I have shown before. This is the same simulation basically. And then, by the way, I should have mentioned perhaps that both white dwarfs in these simulations contain, roughly speaking, about 600,000 particles. So quite many kind of computational elements in both white dwarfs. So we simulate these systems in this code water, and that's a hydrodynamical code. And then we apply nuclear post-processing for these simulations, wherein we take every particle of the white dwarf and we calculate its nuclear evolution. And then after nuclear post-processing, we calculate the moment when is this binary likely to detonate. So the benefit of running these simulations first with the hydrodynamical code and then finding the detonation moment is that we can actually run the systems quite effectively for quite a long time before they merge, and then this way initialize realistically the initial conditions. And once we have found the detonation moment, we then map the simulations into much more computationally intense, but also more robust physically flash code, which is very good at capturing detonations. And here is just a snapshot made by Niranjan Chandra Roy at Massachusetts Institute. And here we see how so this is density of helium only on these two white dwarfs, and here we see how the detonation has been launched on one of the white dwarfs and how helium shell basically explodes, well, basically removing quite a large amount of helium in the binary. In this particular video, we do not detonate the binary, we just see that the helium shell detonates by itself, but doesn't lead to the explosion by itself. But basically, that is the whole point. So we are kind of marking the boundaries of wherein does the helium layer affect the evolution and wherein it does not affect. And that's the subject of our very much soon upcoming paper. And in terms of computation, these sort of simulations were really quite heavy, I would say. So, for example, simulations with this water code was based on OpenMP prescription for, like, roughly speaking, 20 cores or something for several weeks. And yep. So, sorry, I thought I heard something. So at the same time, the flash code was run on a separate machine, which is just adapted to that, and the flash code was run on like many hundreds of cores, depending on the resolution, and that's how computation intense are these sort of problems. And this brings me to the last story, demonstrating yet another quite very different sort of evolution in astronomy. And this is the story about the so-called L3 mass loss and its effect on triple stellar evolution. And that's the project we've been working together with Joris Vos and Maja Vukovic, and also with Silvia Tunen in the triple context. And here, by the way, is an image of a triple system in forming. So actually, it's an image by the radio telescope called ALMA, and here we see how a system of gravitationally bound 3 stars is actually right now forming, and well, eventually it will become a system of 3 stars orbiting each other. So the so-called L3 mass loss is mass loss from behind the donor. So here on the image, you see figures from the simulations by Morgan MacLeod in 2018, and here we see a red giant star. So red giants, we have talked about them before, losing mass to a companion, and this is before the onset of a so-called violent common envelope phase, wherein the red giant loses all of its envelope very quickly over the course of few years, basically. And L3 mass loss is the material being lost from behind the red giant. So on this figure, for example, the L3 mass loss is mass loss from these regions. That's earlier on snapshot, and from these regions is a later on snapshot. And the reason why L3 mass loss is actually interesting or important is that when the material is lost from the back of the red giant, it tends to carry away quite significant amounts of angular momentum, and if one does not account for that, then one does not account for the effect of the angular momentum being lost from the system, and that means that the system's final orbit might be different in calculation compared to what it really is. To put it yet differently, it is important to account for the effect of L3 mass loss from behind the red giant donor to properly calculate the final orbits of systems which undergo quite intense mass transfer. And I'll just demonstrate that based on a simple diagram. So imagine 2 stars. One of them is a red giant on the right, and another one is a small, more compact normal star like the Sun, main sequence star. And on the figures, in the bottom, we see, basically speaking, how does the mass transfer rate evolve over time as the red giant star loses mass to the companion. And on the other figure, we see how the period changes once as the red giant loses mass to the companion. And the thing is that if we take a main sequence star and somehow it ends up being close to red giant, sufficiently close, then the main sequence star tends to pull off gravitationally material from the surface of the red giant. And by the way, these tracks are obtained with the MESA code, and they are evolved basically in as detailed fashion as possible, so to say. So the picture is like that. So if you have the main sequence star, which is somewhat far away from the red giant, or the red giant is not too much affected by the main sequence star, it may be losing some amount of mass, and that amount of mass is going to be relatively small, and that mass can be nicely accreted onto the main sequence star. If the main sequence star is located a bit closer to the red giant, then the gravitational influence from the main sequence star will be stronger, so more material will be lost from the red giant from its surface, and it will be lost at a higher rate. And as a result, if you track how mass transfer rate evolves over time, or how mass transfer rate evolves as the donor loses its mass, we see that the mass transfer rate reaches higher values and the final periods become smaller. And if we imagine a configuration wherein the main sequence star is really quite close to the red giant, and quite a large fraction of red giant envelope is unbound or affected by the influence of the main sequence star, then the red giant loses mass both to the main sequence star in the direction of main sequence star, but also from the back of it, and that is this L3 mass loss, which is happening over here. And the key effect of this L3 mass loss is that because the extra mass has been lost from there, the final period eventually becomes smaller than it would have been otherwise. So here we see it on the plot of orbital period versus mass of the donor, and we see that as the donor loses mass, then it kind of experiences this sort of like a kink. That's the location, or this is the point in evolution when L3 mass loss starts to take place, and then as a result, the final binary has quite a short orbital period because of this kink, so otherwise it would have actually been higher up there. If we imagine that the binaries were actually, or that the main sequence star was initialized even yet closer to the red giant companion, then actually the whole mass transfer evolution would actually be quite violent and very quick, and the whole system would go through the so-called common envelope phase. Now, here is just basically a summary of how this L3 mass loss is modeled in present-day evolutionary calculations. Specifically, currently, there are two approaches to modeling this L3 mass loss. One of them is to assume that L3 mass loss is constant at all times. In other words, that the red giant is losing mass through the back of it from time equal to 0 at any separation. So basically, just kind of assuming that it's just constant, so that some fraction of mass is lost from the back of the red giant. The effect of such assumption is that yes, indeed, we see that. So here are different tracks for mass transfer rate versus mass, and for orbital period versus mass of the donor. Basically, evolution again goes to the right. So as time goes, the donor becomes lower mass, and we see that if we assume higher L3 mass loss, but assume it constant, then we indeed see that its final separation, the binary final separation, decreases. But the problem with this prescription is that really, in reality, the fraction of mass lost to the red giant is, through the back of the red giant is not really constant, because as we saw in the previous pictures, that actually initially red giant, initially red giant might have started to lose mass gently, and then later on could have evolved to this intense regime, and then we can't say that initially there was already L3 mass loss. Instead, in reality, L3 mass loss could only set up or kind of get activated when mass transfer rate, or when the evolution becomes sufficiently intense, or when the mass transfer rate becomes sufficiently large. Another modeling of L3 mass loss currently in the literature was to basically not model it at all until the conditions for L3 mass loss sort of like initialize. And in that case, people just assume that it triggers this violent common envelope episode wherein the red giant and the companion just plunge into each other. So in other words, it was basically about not really modeling L3 mass loss, but really kind of using it as an indicator for some kind of violent mass transfer in the system. Basically what we have done is that we have tried to construct a model for L3 mass loss, which is really based on as minimal number of assumptions as possible. And here on the picture you see a simulation with our oil on water code, which was developed by myself, Ross Church, Melvin Davis, and this code is used for modeling the flows of mass transfer which are sufficiently mild. So in other words, if one wants to simulate how small amount of mass is lost from an object, one would probably be very good off by using this code, because this code is optimized towards transferring small amounts of mass to the companion, and that's impossible to do with another code without using the same technique. So in other words, this oil-on-water code here is an example of a binary. This is a red giant, this is a companion, and in this particular case, the red giant is going around the companion and exactly doing nothing. This is just basically to demonstrate the stability of the code. So basically, nothing is really happening, and the binary is on a circular orbit. And the idea of the code is that the surface of the donor star, or of the red giant in this case, is represented by a specialized type of smooth particle hydrodynamics particles, which are artificially separated from the core of the star. And such artificial separation allows us to do two things. First of all, we are able to model really low density layers on top of other stars, and secondly, we are able to put significantly much more resolution, by a factor of about 10, into the envelope of the red giant, and this way kind of better resolve the things which are happening to the lost mass. And here in the next slide, I show an example of a simulation wherein we took a main sequence accretor and a red giant, and we have been continually changing over time the separation between the red giant and the main sequence accretor. And in this case, we are not visualizing the points which have been passing towards the main sequence accretor just to clarify the view, but we continue to over time really shrink the orbit and kind of make it smaller and smaller. And in this case, the main sequence accretor has stronger and stronger influence over the red giant envelope. And in this case, it's taking quite a lot of material from the red giant onto itself, but also red giant starts to lose quite a lot of material from its back, this L3 mass loss, which you could perhaps see over here. And basically, through the usage of this code, we have been able to quantify really how many particles, or how quickly does the red giant lose mass in its back, and how much angular momentum does that material take. And that has been actually quite useful, because we have been able then to construct empirical graph for how does the mass transfer through the back of the red giant and through the front of the red giant depend on the binary separation. And we have done that, and we have obtained the empirical curves, but at the same time we have also constructed an analytical model for how does that mass transfer rate depend on separation, based on the well, basically equations for hydrodynamics, and just really analytically derived how much mass is supposed to be lost. And quite nicely, the plots here show separation versus the mass transfer rate, and we see that, so one curve, the blue curve, is analytic curve in both cases, and the red curve is the smooth particle hydrodynamics code obtained from curve obtained from these simulations. And we see that actually without fitting, we actually reproduce the mass transfer rates for through the L1 point, which is in the inner part of the red giant, and through the L3 point, which is the back part of the red giant, quite accurately. And we have taken that analytic model and have implemented that model in Mesa code. Mesa code, I mentioned the code for modeling the stellar structure in detail, and this way we kind of have a hold on, or we have an idea of how does that L3 mass loss manifest itself in more general astrophysical situations, just like, for example, in populations. So here are just a few implications. I will just list perhaps the most interesting ones. So first of all, we have initialized the galactic population of objects. In other words, we have initialized the objects with masses as they are really in the galaxy, and with metallicities corresponding to those masses as they are in our Milky Way galaxy. And we have evolved quite a large set of binaries through this MESA code with the L3 mass transfer turned on. And by evolving that, we basically see that this L3 mass transfer, or accounting for it, helps us explain the existence of so-called white dwarf main sequence star binaries, wherein white dwarfs are remnants of red giants, and main sequence stars are their companions, which have stripped the envelopes off from the red giants. And the presence of L3 mass loss, or accounting for L3 mass loss, allows us to explain the existence of particularly short orbital period binaries remaining from a giant mass transfer, and that was not possible to do before, and these systems were quite problematic for other models. L3 mass loss can be useful for describing planetary nebulae resulting from mass transfer, because if we have mass loss from the back of the red giant, we would expect that the planetary nebulae, or especially pre-planetary nebulae, should contain the spirals coming out from, kind of visible spirals coming out from the back of the red giant. And finally, we found that this L3 mass loss basically is, as expected, is important mostly for systems which are kind of extreme, which are able to reach extreme mass transfer rates. And here on the plot, we see the mass of the donor in binaries which we simulated, and on the y-axis we see mass ratio between the donor mass and the companion mass. And basically, typically, when one increases mass ratio, the mass transfer ends up being more extreme or more violent. And here on the plot, the green dots indicate the cases when the mass transfer is not extreme. It's called stable mass transfer. The orange dot indicate the cases when mass transfer is really extreme, and there's this common envelope unstable case forms. Those are unstable systems or extreme case systems. And the purple dots indicate the cases which are not ending up violently, but which still experience L3 mass loss, and where L3 mass loss is important. So, put very simply, L3 mass loss is important for systems which are on the boundary between the stable, simple behaved systems, so to say, and unstable common envelope systems. And finally, we have found that the L3 mass loss is very important for eccentric systems. And the thing is that if we have two binaries, or if we have two objects in a binary, and the stars are on eccentric orbits, then the influence from the other star can be quite significant. It can actually lead to stripping of material from the back part of the donor star. And here I'll just outline the main idea from the implication of this L3 mass loss for triple stars. And the thing about triple stars is that triple stars are commonly known to experience the so-called eccentric mass transfer. In other words, if we have two stars with a triple companion, then the triple companion can ignite, or triple companion can induce eccentricity oscillations for the binary it orbits. And the eccentricity oscillations in the binary which the triple companion orbits make it so that when the binary starts to evolve, for example, when one of the stars starts to evolve, then they will start transferring mass on eccentric orbits. That's the result which has been obtained by Silvia Tunen recently by running a triple star evolution code. And in there, we basically see that, so here are different types of stars: main sequence stars, Hertzsprung gap stars, red giant branch stars, and other stars. And here the bars show the solid color bars show that place where eccentric mass transfer, where the binaries start to transfer mass when they are on eccentric orbits. And basically speaking, the eccentricity of the binaries make, again, the L3 mass loss active, because the one of the stars manages to kind of dig deeply into the other star, and that L3 mass loss in eccentric binaries is actually quite important, because then if a triple companion has induced mass transfer in the inner binary and that mass transfer was eccentric, then those binaries induce L3 mass loss, and then as a result they end up at periods which are much shorter than they would otherwise have. And here's just an example of simulations which we have constructed based on the eccentric mass transfer code by Adrian Hammers, extended to account for the L3 mass loss, and also based on the inputs from the simulations which Silvertooth has performed. And here's just an example of a system which is everything is the same, but on one evolutionary track, the system has L3 mass loss accounted for, and another one it does not have L3 mass loss accounted for. And on the x-axis for both plots is the time in mega years, and on the y-axis is the binary semi-major axis, or binary separation, if you like, here and here. And there's also eccentricity, the binary eccentricity, also over time. And we see that when L3 mass loss is accounted for, the binary separation after mass transfer is really quite significantly lower. It's about 150 solar radii, or it has changed by a factor of 2, as opposed to the case when there is no L3 mass loss accounted for, in which case the separation changes by only maybe 20% or so. So in other words, actually accounting for L3 mass loss allows us to explain, or at least produce, the binaries which are post-triple mass transfer, and we're basically looking for observational confirmations of this scenario, and that could actually be very useful, because that could explain us, could help us explain the triple systems better, but also perhaps constrain the, again, regiant mass transfer better. And here we are at the end of the of these 3 stories. And I guess, again, the 3 key messages I would like just to convey really is that astrophysics is really quite diverse. I mean, so people in astrophysics typically solve problems related to really quite a different set of objects. Kind of, for example, nuclear detonations in exotic compact stars like white dwarfs, or for example, studying galaxies, which are really huge objects of many stars. And so basically, there's really quite a big diversity of problems. And similarly speaking, the computational challenges we deal with are also really similarly very diverse. For example, in one case, one would have to simulate quite a large amount of gas and stars together. In some other cases, one would be simulating many systems. In some yet other cases, one would be simulating many detailed stellar evolution codes together. But in all cases, I hope you can see how high-performance computing is really instrumental, because otherwise, without doing high-performance computing, we'll not be able to basically achieve almost any of the results I've been talking about today. So thank you very much for your attention so far. Thanks a lot.
Great. Thank you very much for the very interesting talk. I think we possibly have time for maybe one quick question. If anyone has any questions, please write them in the chat. I'll just point you to the chat. You can get to the group chat by clicking on the purple chevrons at the bottom right-hand side of your screen. But yeah, if anyone has any quick questions they'd like to ask Alexei, please go right ahead. While we wait, I'll ask a very brief question, which is, so of the 3 simulations you discussed here today, which ones are the most computationally intensive?
I'd say perhaps the most computationally intensive, in my perspective, are the simulations which were actually done on detonations of white dwarfs. So if you remember, there was this video of how the white dwarfs were detonating their helium over here. So specifically, really, one has to be very careful about how does helium detonate and sort of like resolve the elements of the whole binary in quite large detail. And these are 3D simulations which really took, like, depending on resolution, again, up to 1,000 cores at the same time to run, and that's quite a quite a big computational demand.
Okay, great. Thank you very much. It doesn't seem like there are any more questions at the moment, which I realize might be because we overran a bit. Some people have to leave. So I'd like to take this opportunity to thank you again for giving this very interesting talk and sharing these very interesting and varied results on astrophysics, and to thank everyone who's attended for attending. And I hope you all have a good day.
Thank you so much. So long, everybody.